Hey, welcome back to the bunker. Today I work on some gears. I have to modify some gears. These are already modified. And I have to cut two new gears. So we start by modifying these two gears. The gears themselves already were commercially bought, readily hopped gears, but they had to be modified. They had to be bored out, and later we will drill a bolt hole circle. And we need to cut this gear from scratch out of 42 chromoly 4, a preheat treated steel, 4140 HT in the ANSI world. And I already did a test part in Delrin because that's most material I had at hand, and I just wanted to see if there is a minimum number of teeth that a gear can have. And 9 is definitely very, very close to that number. The gear cutter I used is a number 1 cutter. I will talk about that later, and that usually does only a 12 or 13 teeth gear, not a 9. But this is for a prototype and has to be good enough. So seems to mesh. It meshes nicely. It rolls off the other gear nicely. The profile will not be ideal. So, but start at the beginning. First, we look at these gears in an unmachined state. Modifying a commercially bought gear. These are soft steel gears, hopped gears from a supplier. And it's always a good idea with externally sourced gears to check if the pitch circle diameter runs true to the feature that you're about to machine. In this case, I want to use the center bore as a reference for indicating on the lathe. So I put a 12mm dowel pin in here. That's a very close fit, almost a press fit. Rested it on 2 V-blocks, and I take a 4mm dowel pin which hits on the flanks of the gear teeth, and I'm using an indicator in my height gauge to check the runout. I zeroed the indicator out on top dead center of the pin in one position, like this, and I mark the spot as 0. And I spin it about, let's go for 90 degrees. Go 90 degrees, reseat the pin. And do the same thing again. And this is also 0, so far it looks quite promising. I had cases where on commercially sourced gears, the pitch circle diameter was not running true to the bore. In those cases, you have to be very careful and indicate or hold the gear on the pitch circle diameter. Okay, this is minus 10, means 10 microns. And last one, this is minus 15. So we have a total indicator reading of 15 microns, 0 to minus 15. That gives us an overall eccentricity of about 7 microns, and that's pretty decent. For the application this gear is going on, that's way good enough. Here we can see the pin hitting on the flanks of the gear, of the space between the gear teeth. And the indicator tip riding over the pin. When we look closely at this gear, we notice And we have tool marks in here on the teeth, on the sides of the teeth, but also on the top, on the crown of the teeth. That means these gears were cut with a cutter that forms not only the tooth gap in between and the tooth itself, but also the OD of the cutter in one pass. Like a full profile threading insert that also cuts the diameter of the thread. That means the OD of this gear should run through to the pitch circle. So let's check this. Yeah, and now it goes slightly into minus, matching my reading on the pitch circle diameter. So that's a pretty darn good gear for these are very reasonable priced hopped gears. No high precision gears. In some cases, you will see gears that are only machined, that are only hopped or form cut on the gear teeth itself inside here. The crown of the teeth, the top, has still tool marks from turning them. Then usually, depending on how good the part was indicated, the OD does not run through to the pitch circle. So careful there. We could take this gear now in soft jaws and just hold it on the OD, and that would be perfectly fine and run true to the pitch circle diameter and true to the bore. So that's quite nice. But I want to hold this gear down here on this diameter and the 6 jaw. So let's bring indicator down and check this too. And that's a case where we have to be really careful. We can hold it on this diameter, but we cannot indicate on here because this does not run true to the bore, the OD of the gears, or the pitch circle. So we're going to hold it on here and indicate either a dowel pin in the bore or just the OD of the gear. In this case, I think I will go for the OD of the gear. So this is like almost 50 microns, 40 to 50 microns. That's a little bit much. Not going to do it like that. I indicated the gear on the OD of the teeth using the set through of the 6 jaw chuck. And when I jump from teeth to teeth, I'm within the 10 micron range that I had on the surface plate too. So not looking too bad. Now I will just do a last double check with a pin in here. There we go. Top dead center. 0. Turn it by 90 degrees roughly. Indicate again. 10 micron plus 90 degrees. Slightly below 0. And again about 10 micron. So I can be relatively safe now that this gear is running as true as it gets, given the inherent tolerance that's already built into the gear. Double check my thickness here. About 20 micron below nominal. That's perfectly fine. Now we need to get a boring bar in here. So we have a nice 12mm CCMT boring bar here. It's a little bit large for a 12mm starting hole, so I'm pulling the tool a little bit above center so I can take a first roughing pass and widen the bore to get the boring bar in. Okay, I hand feed the first roughing pass to get an idea of how the tool behaves. Now I can drop it down to its normal center height. I'm running through tool air here. This is a small ball valve with a 2.7mm air coupler, and I threaded my boring bar on the backside also for a 2.7mm air hose fitting or air coupler fitting, and I can just hook this up, turn this on, and I have air through the tool. The boring bar is already pre-drilled all the way through and has a channel opening here directly blasting at the insert. Normally this is used for coolant, but especially on steel, dry cutting with compressed air to get rid of the chips helps a lot. At first I set this up. I saw this in a friend's shop. He has a wonderful Troubleshooting 102N VM lathe, and he has the same setup. I thought it's quite nifty, so I copied it for myself. That's very helpful. I think we can power feed it now and also increase the speed. Let's see, this is about 15mm. So we want to run about 150 surface meters, and we have a diameter of 15mm. So we have a speed of 3000 RPM. That's a little bit much. This lathe does only go to 2000, so we go to 1800 because I don't want to spin it that fast with this part here. Okay, that works exceptionally well. The chips get blasted right through the spindle bore out the other end and hitting my milling machine. It seems like I can take a depth of cut of 1mm with this boring bar in the current speeds and feeds without having the lathe explode. So I'm not going to use this flimsy boring bar for final cutting. I'm going to use this 20mm DCMT boring bar in a large heavy-duty boring bar holder that I made recently. The boring bar, not the boring bar holder. That's a commercial one. So you saw that it's, I went to quite a bit of trouble to make sure that the pitch circle of these gears runs true to the bore that I put into the parts. I'm quite happy about the finish. These are C45 steel, which is a 0.45% low alloy carbon steel, or plain carbon steel. I have these two done, only need some drilling, but we will do that later. Now we have to talk about this thing here. This is going to be the small pinion for these large gears, and I'm not too happy about cutting a 9-teeth gear, but that's what we have to do. This is the 3D model the customer supplied. I pulled the drawing off the 3D model. I also I pulled out all the important drawings, and we'll go over to the milling machine because I already prepared the blank on the lathe out of 42 Chromo 4. Here's the setup. Walter UTA80 dividing head held in the vise. I have the original Walter small diameter 3D charge chuck on here. It runs reasonably true. It runs really decent. With some tweaking, runout out here is basically 0. And this is the blank I prepared. We're going to cut both gears at once, back to back. One gear here and one gear here. I machined this section here with a part-off blade. And that means that we have to cut only one gear. And then we put this back in the lathe, indicated true, and then part it off in the center. Then we grab it on this short section here and bore them. And at the very end, we have to even put a key slot in them. So these are fairly intricate parts. This is the Module 2 number 1 gear cutter out of Soviet production, as I learned recently. Not even high-speed steel, this is just tool steel, so we have to be reasonably careful not to burn it up. And I reground this. I made the last video I did, or one of the last videos I did, is showing how to regrind a relief turned gear cutter. How do we get the cutter on center line? Well, that's not too complicated. We drop it onto a known diameter like this small diameter here. We touch off on here very lightly, and we zero out the DRO. I mic'd this cutter, it's 8mm thick, so we drop down 4mm, that's half the thickness of the cutter, and then we drop down half this diameter. This is 12.9, so we drop down 6.45, and now we're on center line. Assuming that the profile on the cutter is ground center to its thickness, but at some point I have to take assumption. And when I line up one of the tips of the cutter with the central knob of the face turned part, it lines up very close. So that's good. That's our depth that we're going. We're going to conventional mill. Means cutter goes in this direction and spins as usual. I don't dare to do a climb cut with such a large profile cutter. That's a lot of cut force and will probably end up in a crash, so we're not going to do that. We want 9 teeth and our indexing head is 40:1, so we put 40 up here divided by 9. We don't have that's basically 40 holes on a 9-hole index plate. We don't have a 9-hole index plate. So let's multiply this by 2. Then it's 18. So 80 holes on an 18-hole bolt hole plate. I don't have that either. But I have 27. So 9 times 3 is 27, and 40 times 3 is 120. So we have to go 120 holes on a 27-hole index plate. 27 fits into 120 4 times and gives us 108. The rest, 120 minus 108, is 12. So we go 4 full rotations on the hand crank and 12 holes on a 27-hole index plate. Easy, huh? Okay, to get our angular division, we have to do 4 full revolutions. 1, 2, 3, 4. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 down here. And as you can see, I already set the sector arms, so I don't have to do the hole counting all the time. I go to the last hole before I hit the sector arm. That's my position. Then and then do not forget to move the sector arms up against the index pin again. Just spin it over, and then you can start again. 1, 2, 3, 4, and 12 holes. Okay, that was quite a lot of milling, especially as this is the second part I made. That's right, I messed one up. Here's the first one, and usually when you mess up an indexing job, it's because you actually messed up the indexing itself. You miscounted, you skipped a turn on the hand crank or something like that. But in this case, it was something really stupid. The lock of the quill was not tightened properly, and the quill creeped up about 1 millimeter during one of the passes. And when you measure the thickness of the teeth, there is a difference of quite a lot, like 0.2 millimeters from tooth to tooth. So I noticed it, took the part out, goes in the shelf of shame, machined a new one, still had the lathe and all the tooling set up, luckily, so that went quite fast. And then I recut all the teeth, and this time my quill stayed in place. So this is preheat treated material, comes at about something like 1300 newtons per square millimeter of cross-section tensile strength, and it's relatively tough. It's a tough material, and it's quite hard with a large form cutter on this lightweight machine to get it done. But and when you watch the footage of milling the teeth, you can see quite a bit of movement in the mill. That's mainly the vertical column twisting in itself. The indexing head itself is rock solid. It has a large tapered plain bearing in front, and when you lock it, the bearing gets pulled into the taper seat and locks the spindle solid. So the indexing head is not the weak point in this case. Now we check the depth of our teeth. I already adjusted it. And we do that by inserting a pin in here, and we measure against the outer diameter of the gear. And I know from the CAD drawing that the height from the OD of the gear to the top of the pin should be about 1.1 millimeters. So the OD of the gear is 22 millimeters, and we read 23.1314 here on the micrometer. So 23.14 minus 22 is 1.14. And when we look at the drawing, I inserted a pin here, a circle that resembles a 4 millimeter dowel pin or gauge pin, and I dimensioned off the center line to top that center of the pin, which is 12.14 millimeters. That's the way this gear was modeled, and I put the pin in. And it's easy to measure because this gear has an uneven number of teeth, so I can measure from top dead center pin against the OD of the gear. And the difference between the OD and the top dead center is 1.14, and that's what we measured, so hit my dimensions quite okay. If the gear had an even number, I couldn't measure against the OD on the other side of the pin. I would need 2 pins and measure from pin to pin. I cut off the gear from its stock. Now I'm holding it in a 22mm collet, which is the OD of the gear. In this case, as I machined the OD of the blank and I indicated it true, and I know that it ran true when I cut the gears, I can use the OD of the gear to hold on to it and know that I'm running true. So I'm using part-off tool, 2mm wide inserted parting tool, to split the gear in two separate pinions now. And this starts obviously out as a heavy interrupted cut. Okay, parted it off almost completely. I don't want to have the gear drop free and roll all over the place. So I'll leave usually a small rest of material and just break it off. Almost last step is to cut a 3mm keyway in here. I have a 3mm slotting tool in the quill of the machine and the spindle. It's aligned in the X direction, so it's cutting correctly. I already did the first one, so I'm already centered over my part. And now it's just a matter of stepping over, taking a cut, stepping over. You have seen me doing this numerous times. I'm stepping over about 50 micron per pass. And you might notice that I did not lock the spindle against rotation. And the simple reason why is because it's in this case absolutely not necessary. This tool cuts on center, it's square, and there is no force in the cut that tends to turn the tool. There is no rotational component in this cut. So you align it and then you just leave it alone. And no, I'm not worried about wearing out the quill bore of the mill. The cutting forces with this process are very light. The tool is at ground, so the axial force comes in very close to the center line of the quill. It's only a very, very light cut, and running a large fly cutter with a very long extended quill on something like a Bridgeport is probably way worse for the machine than this. So I zeroed out the dial caliper, the digital caliper on the bore diameter, so it's 0 at its diameter, and I know the height of the key slot from my CAD model that I got. So I can measure it like this, and it should be 0.6 millimeters, and we got 0.63, so we're good. And there we go, 2 gears with 3mm very shallow key slots. Don't comment on the design, it's customer design. I know the background behind this design, and there are very strict size and room and distance between the shaft restrictions, and we couldn't figure out a better way than this. This has to do, this is a prototype, so we're going with it. Not a 9-teeth module 2 gear is not the ideal solution, but it's all we can do right now, so we're trying this. And you get some gear cutting and machining footage, so it's a win-win-win-win, I guess. Okay, here is the slotting tool. I ground it to 3mm width in front here. Then I relieved all this material here just in the thickness. So in front here it's 3mm. That's the cutting end. And the relief shank is only 2.4. This surface here is a little bit tapered to the back. Here it's 3mm and back here it's less. I put about 1/2 degree of back taper on here. And back here it's only 2.8, and in front, as I mentioned, it's 3mm. A little bit of positive rake here, so it's cutting. So it's cutting a little bit softer. Don't make this angle too big, otherwise the tool will tend to dig into the work. This is about 3 or 4 degrees. And here a little bit of clearance angle, so it doesn't rub when it goes down like this. 1, 2, 3 degrees, that's fine. As usual, when I do slotting, I put a shaft collar on here, so the tool doesn't get pushed up into the spindle of the mill, or into the collet mill. So, while we're here, we can look at some of my slotting tools that I ground in the recent time. This is a very narrow slotting tool. This is a 1.7mm slot. And I use this just to cut a clamping slot. So this is my vise stop, and I use this slotting tool here to cut this blind slot here, which goes from here to here and does not exit, so it's not a band sawable or a circular sawable slit. A little more elegant than an open-ended slot for a clamping situation. And there's just a pinch screw that pulls it together and holds my vise stop together. Looks kind of clean. 60-degree slotting tool with a 1mm land. This one was for a spline drive, did a video on that. 60-degree with a 0.2mm land on here. This was used to cut the spline drive sockets quite some time ago. Large 5mm keyway tool. So this last slotting tool, this is probably the coolest. This is a carbide shank, solid carbide, all the way up to here, and you can see the braze joint, the silver solder joint, and I have a piece of high-speed steel cobalt 10 silver soldered onto the end of the shank and ground into shape. It has the same small cutting angle, relief angles in all directions, but it has a solid carbide shank which is 3 times stiffer than a steel shank. And I needed this because I was slotting all the way this whole length in steel, 5mm wide. That 5mm width is probably almost the limit what I'm comfortable to do on this mill in one pass. And otherwise I would use a 3mm slotting tool first, and then take the tool out and put in, for example, an 8mm tool. So it reduces the cutting forces. What works pretty bad is stepping over with a slotting tool. That's bad. These tools are very stiff in this direction because they have a very large cross section here, but in this direction, side to side, they're very weak because very thin cross section. So stepping over to the side usually ends with a very shitty, with a very bad keyway. Bell mouths on the start, and just not a good job. Better use increasingly larger slotting tools. So that's slotting tools, and I keep them around when I'm finished with them. So for the next job. While I deburred the holes in the gear, I thought I could do a little bit of content on countersinks. I have 4 types of countersinks here. These are the common ones that I tend to use. These are the single flute with the cross hole. These are really only good for light deburring. They are not for doing a proper countersink in my mind. They work exceptionally well in a cordless drill. I don't like them on a machine tool very much. Not the cool. I just don't like them too much. Standard 3 flute countersink. That's what a lot of people are familiar with. Evenly spaced 3 flutes, high-speed steel, work very well. You run them relatively slow and you feed them relatively hard, and they will leave a very nice countersink, usually. They can be troublesome. Sometimes you have just a setup that is not cooperative. You get chatter or out of round countersink, stuff like that. Can happen. Takes a little bit of practice and feeling for these things. Next step up is basically the same, but with unevenly spaced flutes. So these have a tendency of almost never chattering. Very expensive though. Coated, I bought this years ago and it's still perfectly sharp. When you look at the coating under a microscope, it's still fine. Worth its money. And then the coolest one is probably this one here. So this is a normal, this is a 3-fluter too, but it has spiral flutes. Goering makes these, Goering Spyro, they are called. They are not cheap, I will say that. But they are not that expensive that you might think. So these are really cool. They cut very free. The flutes are uneven spaced. When you look at the size of the flutes, they are not the same all the way around. And due to the spiral geometry, they cut so soft, very little cutting pressure needed. Even in something like a 303 stainless, or even a 316 stainless, if you run it at a slow speed, it will not chatter. Give it a little bit of pressure and it will just cut a nice countersink. These are brilliant. So that's my 5 cents on countersinks. It's basically like this. Okay-ish, okay, very okay, super okay, something like that. These are really cool. Okay, got the parts finished. Large gears have been machined and drilled, bored out and drilled. And the small ones machined completely from scratch. As per request of the customer, we added a M3 set screw, thread for a set screw, opposing side of the keyway. We will see how these hold up. So at least they run quite okay-ish on each other. The geometry on these is probably completely off now, as we went with a way smaller tooth count than the cutter is actually designed for, but for a test part it probably will work out fine. So, hope you enjoyed. Thank you all for watching, and I'll be back.